Welcome to the third narrated demonstration for the Marine Community Ecology course at UTMSI. Today's session is all about data visualization using ggplot. So ggplot2 is a wonderful package that allows us to plot data, which is something we encounter quite frequently. So today is all about understanding how to make plots and also how to make them pretty. The ggplot package, the GG in it stands for Grammar of Graphics, which is something you may or may not want to remember. But the bottom line is that it offers an extremely versatile set of functions to create really nice data visualizations. And the thing about ggplot is that it works with layers. And these layers are the data, the aesthetics, your geomes, the axes, and the descriptions. So to dig into that a little bit, the basic concept is such that we start with tidy data, and tidy data always means that our variables are columns and our actual data are rows. And we feed ggplot, the ggplot function, the data first. So in our case here, that would be tidy data. Then we map aesthetics onto that plot, and we do that using the AES function right here. And in the AES, we have to specify the x-axis, which is our v1 in this case, and the y-axis, which is our v2. And then we can specify other elements as well, and I'll show you exactly how to do that later. After that, we're plotting what's called the geometry, and that hides in these geome functions in ggplot, so geome point or geome box plot or geome line. And that's really the type of visualization that we want our plot to be. After that, we can fiddle with the coordinates and the scales. So that gives us a bunch of different options, such as rescaling our axes, or flipping our axes, or changing the scale we're looking at. And then finally, we can mess around with the labels and the tick marks and the breaks and everything, or the legends. So it's really quite a versatile way of approaching data visualization, and I personally love ggplot. Okay, so the package is the ggplot2 package. I don't know if there ever was a ggplot1 package, but this is the ggplot2 package. It comes by itself, but there are also a lot of auxiliary packages such as ggridges or ggally or ggeffects. And it integrates really well with some other packages as well that are tailored to grab plots or work with plots from ggplot, such as Patchwork, or the Visualize package, which is a package that we developed to let you plot your data using the color palettes provided by Mother Nature, more specifically fishes. So make sure you have these packages in your environment. So you can use the install packages functions right here to install these. You may have to grab Visualize from the World Wide Web. If you just search for Visualize online, you'll find instructions on how to download it to your hard drive. And then just make sure you call these packages as well, using the library command. And then just a little bit of preparation. We're going to be using two datasets today. The first one is the herbivore traits dataset. Most of you, if you've followed along, should be pretty familiar with that. Should be in your data folder. If not, you can download it from the website directly. And then we also have a refish dataset, which is also available. If you just scroll up a little bit, you can download it there and import it into your data folder. All right, let's get started. Now, the ggplot function itself actually doesn't do much at all, except for providing you with a blank slate. So if you just create a plot called P1 and you tell R that P1 is supposed to be a ggplot, by just running this function, you essentially get this blank canvas right here. Okay, this is just a blank square that has nothing in it. It's just a ggplot plot without anything on it. We can add data to that ggplot using the data argument in the function. And if we do that down here, we feed it the herbivore traits data set. You can see when I call the plot on the right, and all of these slides are going to be structured the same with the R code and the instructions on the left and the plot on the right. You can see that nothing has actually changed. It's still just a blank slate, but now that blank slate actually knows where to find data. So it's connected to this data set, which is really important. And now we can specify our aesthetics, or basically direct ggplot to where in the data set we have elements that we want to plot. So AES, the AES argument in the function down here, it clarifies which columns hold the information that we want to use. And so in this case, for example, we want to use we want to look at the relationship between body depth and eye diameter, with body depth on the X and eye diameter on the Y. And as you can see on the right in the plot now, we have an X-axis that's called body depth and an Y-axis that's called eye diameter. They're both to the scales that the data actually occupies, but there's no data in here yet. And the reason for that is that we haven't specified the geometry yet. So far we've only told ggplot where to find the axes that we want in this plot. Okay, so let's add the geometry. We can simply start by using points. So this is a simple scatter plot, XY scatter plot. Most of you will probably be familiar with that. And that's called using this geom point argument in ggplot. And when we do that, what we get is not necessarily a work of art, but it is very informative. We can now see that there seems to be some kind of relationship between body depth and eye diameter just by plotting the points, the actual data points on here using the geom point function. And now we can start playing around with the visual elements here a little bit. So what we're doing here is in our geom point function, we're changing the size of the points to be size 5. We're changing the shape of the points to be shape number 18. More on the shapes and their specific numbers later. And we're changing the color of these points to be blue. And what we get, instead of the black small dots we had earlier, we get these blue diamonds that are a lot larger. Now it's often really useful to map different group memberships onto your plot using different colors, different shapes, or different sizes. And that's also done in the AES function. Sometimes just because people get confused with where the parentheses are or where the commas end. If you specify columns outside the AES argument, ggplot will throw an error, and it won't actually work. It tells you that it can't find that column. So only if you're in the AES parentheses will ggplot accept a grouping column. Okay, so you can see that here within our AES, we say that now we want the color to be representing the family. So color equals family. What we have to do as well is delete the color argument from the geom point down here from outside an AES function, because otherwise that would override our color argument. And you can see that the plot itself, now we have those 4 different families that we have in the data set, and each of them has a different color to it. So very informative, very useful, happens all the time that you need these group membership assignments. We can also do that with multiple options. So we have shapes, sizes, colors, or fills. Fills and colors are somewhat different. We'll get to that later. But what we're doing here is we're also specifying the shape to be a different variable in the data set. Actually, this is kind of confusing here because there's a column in there called size, and then I realized that we have size down here. So this is a good reminder that you shouldn't name variables after functions in R. Regardless, we'll soldier on. You can see that the shape here has changed based on the size class variable in here, where, for example, the squares are small and the circles are large. And again, we had to remove the shape argument from down here. And then we can also use continuous variables to map them onto the group aesthetics. So in this case, we are adding a third layer of information, which is the standard length. Obviously, it's a little bit redundant because we already have size class in there, but it doesn't matter for this purpose. You can see that we had to remove standard length or SL from down here. Otherwise, it would again override this argument within the AES argument. And we can see that our standard length has been mapped onto the plot, with the smaller plots being smaller fish. And of course, you can also see that, for example, our extra large species down here in the plus, they also have the largest symbol, which makes sense because, again, this is a redundant argument, but it's still nice to visualize it that way. Now, there is a lot going on in this plot. So sometimes we want to break up the information from a single plot into multiple plots. So for example, here it becomes really difficult to actually get the patterns off it because there's so much going on with different colors, different shapes, different sizes, and so on and so forth. We can break up information by groups using multiple panels, which is really helpful. And we can do that using the facet grid or facet wrap argument in the in ggplot. So we're using that plus again, and we're adding this facet wrap argument to it, and we're telling it that it's period over family. You can play around with the arrangement. You can also do family over period, which changes the arrangement of the plots. But what it does, it creates a plot for every single family, and it declutters the plot a little bit, which is quite nice. So that's a way to sort of show different groups and the data within these groups in separate panels that are all really nicely standardized. So very useful function in ggplot that I use all the time. Okay, so far so good. We've done some honest work here, which is nice. Let's jump into the exercises. I would, if you're watching this and following along and trying to get better, I would encourage you to pause the recording right here and try to complete the exercises yourself. So you can read in the coral reef herbivores .csv file that I called herbivore traits in here. And then the exercises are to create a scatter plot with ggplot2, where X is standard length and Y is body depth. Change the points to be black triangles, which is accomplished using the shape equals 17. So 17 are nice triangles with size 4. Remember, one of them, both of them actually will have to be specified outside the AES argument. Then change the color of the points to reflect different genera. So the genera information is in the genus column. And then break up the graph into panels based on different size classes, which are the categorical sizes, the small, medium, large, and so on and so forth. All right, solution. So the first one's fairly simple. We just do a scatter plot using the geom point geom with X equals SL and Y equals body depth. If we change the points to be shape 17 and size 4, then we get these bigger black triangles. Then we add color equals genus into the AES argument up here. So that gives us group membership based on the genus column. And we can see that this results in a nice little skittle color plot with lots of different colors. And then finally, by doing facet wrap period over size, we get these 5 separate panels according to the size classes. Hope you all got that. All right, so let's talk about summarizing data in your plots. So if we're reinvestigating the plot we made earlier, then we see that if we just focus on the y-axis, we see quite a different spread. The eikenthurds are sort of between 0.2 and 0.4. Labrids are much lower, and then the saganids seem to be sort of the largest in terms of the eye diameter. Kyphosids are way down here, and this is great. So we might want to actually show that more specifically. Differences in eye diameter between the four families. And that can be done using categorical axes. At least in marine ecology, marine community ecology, we see that quite often, that we will need a categorical axis. And that's very simple. You just specify an axis that has categorical values in your AES function. So in our case, this would be x equals family. Family are words, so they're a factor or a character vector, and it automatically recognizes that now these are actually categorical variables. So if we do that and we do a geom point again, which is the only one we've learned so far, we see that we have lots of points spread along here across the four families. Now that's somewhat informative, but it's definitely not the best way of visualizing it. We have lots of overlap in these dots, and it's not very clear at all. One way of making it a little clearer is by slightly adjusting the horizontal positioning of each point, and that is called jittering. Put a little jitterbug down here. So that can be accomplished using geom jitter instead of geom point. And you can specify the width of the jitter that you want to apply right here. So width equals 0.1 essentially just adds a random value to the horizontal positioning of the point with a range of 0.1. So it just sort of, adjusts the points slightly based on their horizontal positioning. That's a little bit clearer, a little bit nicer. At least the points don't overlap as much as they did in the previous plot. So they're spread out and they're more visible. But it's still not really telling us much about the difference. And a much better way of doing that, actually showing the difference between those families, would be by plotting the distributions of these points in a proper distributional geom. And the first one we're going to look at are the box plots. So this is a very typical way of displaying data distributions within categorical grouping variables. And what we're going to do here is simply, instead of geom point or geom jitter, we're going to use the geom box plot function here. Now, box plots are very commonly used. A lot of people don't actually know what these boxes mean. This horizontal line here is always the median. The actual box are the first and the third quartiles of the distribution. And then these whiskers here, what they're called, are 1.5 times the interquartile range. So it's essentially 1.5 times the box's range. And then we have these points here, which are the outliers. So they're the points that lie outside of that interquartile range. Very common way of plotting distributions, and a fairly good way because it tells you a lot about how these data are actually distributed. And we can see from here, if we're just comparing sort of the interquartile ranges and the medians, we can see there's a very clear difference between the zygonids and the labrids and the acanthurids. And the kyphosids for that matter. But also note that we don't actually have a box plot here. We just have a single line, and that's of course because we only have one species, and you can't really get a distribution from that. We can make these boxes a little prettier. So the fill of the boxes is generally set to white. So here the boxes are filled with white. We can change that using the fill argument. So up until now, we've only dealt with the color, and the color is always the lines in a plot, whereas the fill argument, as you can see, has now replaced this white content here with colored content. So fill equals family will do that. Note that I'm specifying color equals black here. So that actually, makes sure that the outline of these boxes is still black. I could specify that to be any other color as well. And then I'm also, just a note here, specifying notch equals true, and that just creates this little notch that goes towards the median, which just gives you a little more information about the distribution again. So that's quite a nice plot, shows you a lot about the data. But we can also branch out and use what are called violin plots instead of box plots. And they're nice because they actually show the entire distribution of the data. The first thing you'll notice is that we've lost the kyphosits. So while the box plot can still plot just the median or the single value from a single point in the distribution, violin plots don't do that. But that's not a big deal right now. We're just going to accept that for the time being. And then the other thing you see in these violins, or these sort of distribution density distributions, are these lines, and what these are quantiles, and we can use in the geom violin function, we can specify which quantiles we want. Here they're essentially the median and the 95% confidence intervals, specified as 0.05 and 0.95. And again, we filled them based on the families, which looks quite nice. We can also actually combine multiple geoms. So just because you're using one doesn't mean you can't use the other, which is nice. ggplot is generous like that. So in this case, we're combining the geom violin that we've just used earlier with a geom jitter that we're using to plot the raw data. And this is actually a really good way of showing data because it shows the combined distribution, but also the raw data that forms this distribution. And this sort of overlaying of a distributional geom with the raw data is what's called a SENA plot, and those are really good ways of showing data distributions. Finally, we can also use what are called density curves. So these are, in this case, ridges, density ridges, and for these, it's actually quite nice to change the orientation or to flip the axes. So now we have eye diameter on the x. Previously, as you can see here, we had eye diameter on the y. Now we have it on the x just because we want our ridges to look like a mountain range. And the other thing we've done here, we've used the geom density ridges function, which is part of the ggridges package. So if you throw an error here, it might be because you didn't install the ggridges package. So we've combined that geom density ridges function with the geom jitter function. And we also changed the jitter from width equals 0.1 to height equals 0.1, which jitters it on the y-axis instead of the x-axis. And then the other thing we've done here, just because it makes the ridges look a little nicer, we've adjusted what's called the alpha for the geom, and that just means that it is now the opacity of the fill has been adjusted to be 0.75, so 75%, and otherwise 25% transparency in these, and you can see that they're sort of transparent now. So that's a very nice plot. If you've made it this far, you're almost a pro with plotting in ggplot. There are several other distributional geoms, such as geom histogram, geom density, or geom half-eye. A lot of them hide actually in an ancillary package called Tidy Bayes, which is a super nice package to plot distributions. And again, distributions always mean that we have some kind of spread of values over a certain range. The paranormal distribution doesn't actually exist, but I thought it was funny. Okay, let's get into some exercises. Again, if you're following along and want to get better at this, I would encourage you to pause right here and try it on your own. We're using the same data set, and this time we're trying to examine the eye diameter across different size classes, so that's the size column, using a violin plot with eye diameter on the x-axis and size class on the y-axis, with quantiles set to 20%, 50%, and 80%. You can then fill the violins with colors based on size class and reduce the opacity to 50%. And then you can add the raw data points with the different shapes symbolizing different families. Okay, here's how that can be accomplished. So we're using the herbivore traits data set, and we're setting the x-axis to be eye diameter and the y-axis to be size class. And we can immediately see that, the extra small fish right here seem to have pretty large eyes compared to the rest, especially when we're looking, for example, at the very large species. We used the geome violin geome, and we drew the quantiles at 0.2, 0.5, and 0.8. Those are the values I specified earlier. We can then also include the fill equals size. So somewhat redundant, but it makes the plot look a lot nicer. So now you can directly see the different colors here. They're also in the legend over there. And then we adjusted the alpha to be 0.5, and that gives it this 50% transparency that we're seeing here. And then finally, we're adding points with shape equals family. So you can see right here, I actually specified the AES within the geome point rather than adding shape equals family up here. You can do it either way. Either way works. Sometimes it's necessary actually to draw the AES into the geome that you're working in. And sometimes it doesn't matter at all. Just something to be mindful of. And you can see it added those points with the different shapes. Should have probably jittered it, but it's okay for now. It's just an exercise. Okay, let's talk about uncertainty, and more specifically about how we can plot means and errors. So that's a very typical data format as well. It doesn't actually, if you use tidy data formats, it doesn't actually happen all that often that you have means and errors to plot, because we'd rather just plot distributions. But if you have to plot means and errors, historically what people have done is go to the classic kind of bar plot. I've made the woozy face right here because, as you'll see in a second, I'm not a big fan of bar plots. Okay, so to get there, we actually have to wrangle our tidy data a little bit. So we have to go away from the format that we like. To do that, we take the herbivore traits data set, we group it by family, and then we create some summary values. So we get the mean of the eye diameter, we get the standard deviation, and we also get the n, the number of replicates within each group that produces the mean and the standard deviation. And then we're using a simple mutate here to calculate the standard error, which is just the square root of the standard deviation divided by the sample size. So that's a pretty common formula. And then, just because we want confidence intervals instead of standard errors, we're using these calculations here. So this is lower.ci. That's just what we're calling it, is the mean eye diameter minus the quantile, and so on and so forth. Not going to bother you with it. You can just copy and paste this into your R if you want to. Not much to learn here necessarily. And then what we get is a data set that just gives us the family, the mean, and we can plot this using the geome bar function. And the important part here is we have to specify stat equals identity. And that just means that we have already pre-calculated the mean, and it gives us this bar plot right here. Now that plot wasn't fantastic because it only gave us a mean value. We always want to make sure we plot uncertainty around it. And we can do that using the geome error bar function. So geome error bar takes a minimum value and a maximum value. And in this case, so this is all the same as we had in the previous plot, and then we add the geome error bar to it. And again, we have an AES aesthetic specified just in this geome right here, where y min, or the minimum on the y, is our lower confidence interval, and our y max is our upper confidence intervals. And these are the variables we created earlier in the mutate function. And that just gives us our 95% confidence intervals right here. This is better than it used to be. At least we're showing some uncertainty, but they're still not great, to be honest. A nicer way of showing means and uncertainty or confidence intervals are what are called caterpillar plots. So they're plots that have a mean value or median value, whatever it is, in the middle that is shown by some symbol. And then you have these lines, the whiskers or whatever you want to call them, around it that shows the uncertainty. The reason it's better than a bar plot is because a bar plot always kind of suggests that it comes from the bottom up, showing a range more or less, which these at least don't do. Caterpillar plots are made using the geom point range geom, and very similar to the previous one, you have to specify a lower and an upper value for these lower and upper confidence intervals. The other thing I've done here, just to demonstrate that, is I said shape equals family as well, which you can see it changed that symbol for the mean, which is quite nice. If you have multiple groups again, or two groups that are sort of crossed, you can work with the shape, which you can't do in a box plot. Or bar plot, I should say. And this is just my general opinion. If anybody's trying to convince me otherwise, please go ahead. I don't like bar plots. Do I have them in my papers? Yep, absolutely. Do I like them? Absolutely not. Okay, so we've gone through the major ways of visualizing data. So now we can look into how we can make these plots a little prettier. So far, they're okay, but they're not necessarily particularly pleasing on the eye. So we can work with different colors, shapes, and different themes. I'm already much happier looking at this plot, just getting rid of the ggplot standard default color scheme, which is, in my opinion, absolutely hideous. So we can change the colors using scale fill or scale color as a plus argument in your ggplot. So basically another layer in your ggplot. If you want to get an overview of all the colors that are available in R, you can go to this link, just follow this link in the slideshow. You can get any color you want in R, but these are the colors that are actually named in R. Okay, so let's break this one down. We're using the herbivore traits data. We have family on the x-axis, we have eye diameter on the y-axis, and we're filling these violins based on the family. We specify the geom violin, and we have our quantiles right here, 0.05, 0.5, and 0.95. Then we're adding a geom jitter right here for the raw data. This is the CINA plot I mentioned earlier. We're specifying the points to be white, just because we can. And then we're also making them slightly translucent with an alpha of 0.8. And then here's where the magic happens. We say that our family fill values should be different from the default hideous ggplot color scheme. And we're doing that by scale underscore fill underscore manual. And we can spell out the values right here. I just chose 4 different ones that I thought looked good, which is steel blue, yellow green, dark orchid, and goldenrod. You can't actually see the yellow green except for here, because again, we're losing the kyphosidae in our plot. But in my opinion, these colors already make a huge difference. Now we can also change the shapes, of course. So this is very similar to how we change the colors or the fills. And this is done using the scale shape manual function. The important thing is if you go on the overview of shapes right here, you'll see that these shapes, there's I think some 36 or some total. Not all of them will take a fill argument. So we got to be careful with that. But let's see how we get to this plot right here. This is the same as it was in the previous plot. And then we're adding the shape equals family to this as well. Then these are again the same. We're drawing the same violins. And now in our geom jitter, I set color equals black and size equals 3. Now what that does, I mentioned earlier that color always refers to the outlines. So you can see how we have a black outline here. And then we're specifying the same scale fill values as we did earlier. So because both the geom violin, and then we're saying scale shape manual, and the values are 21 to 24. So those are the symbols number 21, 22, 23, and 24 in the symbol library, again, which you can look up right here. And there are these fillable symbols. 21 is a circle, 22 is a square, 23 is a diamond, and 24 is a triangle. And because they are fillable, the fill argument right here, fill equals family, applies to these shapes as well. So they're being filled with the same color. I don't have to rehash this. It just takes the same fill color values for the shapes as well. Had I not specified scale shape manual right here, my fill argument would have actually not done anything, because the first 4 symbols, which it takes by default, so it would take 1 through 4, they don't take a fill argument. Okay, so if spelling out the colors is too difficult, which sometimes honestly it can be if you have a lot of different colors, you can use some predefined color scales, which are quite nice, or color palettes. And with these color palettes, you can often have them either as discrete values, so discrete colors for every category you have, or a continuous color palette. So one example is the Viridis color palette, which is actually available just in R. You don't have to install anything for it. It just comes naturally. We're working with the exact same plot that we worked with earlier. So this is all the same as on the previous page. But what we changed here, instead of specifying 4 separate colors, we just said scale fill Viridis D. The D here stands for discrete. So that means we have categories. We want discrete color values for these four family factors. And then we have the same scale shape manual argument as earlier. And you can see that it changed the 4 colors to the Viridis color palette, which is this color palette that goes from a deep purple to a really sort of bright yellow. It's quite a nice color palette that I think is quite useful and also quite colorblind friendly. Okay, and then just because we're playing around here a little bit, I'll introduce you to the Visualize package, which is a package that we wrote a couple of years ago. You can follow the link right here if you want to get to the website of the Visualize package, which I strongly recommend. And it works on the same principle. This is a package you have to install, so you have to install it and then load it, as opposed to the Viridis color palette. Again, everything is the same over here as well as here. The only thing that changed is the scale fill fish _D function. Earlier that was the Viridis function. And then we have to specify in this package, we have to specify which an option, and that option tells the package which fish species we want to model our color scheme after. So this is Centropyge loricula. This is a dwarf angelfish species. You can actually see it. It's the one that is in the logo of the Visualize package. And you can see its color palette right there, from this sort of Bordeaux color or maroon color to this black. And as you can see in our plot, it kind of went along this color spectrum from this maroon Bordeaux to the black. Now this color is not in the fish, but the issue we're having here, well, it's not an issue, but what it did is, technically each of these palettes has 5 base colors, but our plot needed 4. So it kind of went in between those different colors, and that's how we ended up with this gray color right here. We can also use continuous color palettes. So if we're plotting continuous data, we don't have categories. That's quite useful. So here we're plotting body depth versus eye diameter, and we're telling ggplot that we'd like the fill to be adjusted by standard length and the shape to be by family. We're adding a geom jitter with a black outline, color equals black. And then we're saying scale fill fish And the option here is Trimma lantana, which is this beautiful fish. This is arguably the most beautiful fish in the ocean. It's about an inch long and it's absolutely gorgeous. And of course it has a color palette in the visualize package. And you can see that this plot right here, we have these values that are very large. So this is standard length of 400 plus. We can see this Bordeaux color, and it goes into this sort of cyan color of the very small species, which of course you can see here in the fish's head. So it's fun to play around it, but this is a continuous color palette where we don't have discrete values, and you can just see the spectrum right here that it was modeled after. Okay, and then we can also work with some of the predefined themes that ggplot has. So in this plot right here, this is the standard, this ugly gray box with the white grid. We don't have any axis lines. It's actually quite ugly, and I don't know why this is the default, but thank God it's easy to change it. And we can do that using the theme _BW, or stands for black white, theme classic, theme minimal, or really any theme. There are a lot of themes out there. You can create your own theme too if you want to. And all that does is it sort of changes some of the basic aesthetic features of the plot. You can tell here, this is the theme classic, so we just added this onto the previous plot with a plus. And the theme classic doesn't have that background, the gray background. It doesn't have the grid lines. It included axis lines that are black. So to me, this is aesthetically much more pleasing than the previous one. But, you know, some people might disagree. So you can play around with the different themes here if you want to. Okay, let's talk about scales and labels on your plot. And to do that, we're going to dip into a new data set, also because we're a bit tired of those herbivore morphological traits. So we will work with the reef fish data set. Again, you can find that using the link on this companion website. And what this data set has is about 6,000 species of coral reef fishes. And then we have the family and the genus and the species, of course, and then we have the year that that species was described in, so whenever it became known to science, the depth at which it exists, so its maximum depth, its maximum size, so this is maximum body size, and whether they're considered a cryptobenthic or a mobile reef fish. You can see right here, so this is the category column, and it says Acanthurus tristis, which was described in 1993, is reef associated, lives to a depth of 30 meters, has a maximum body size of 25 centimeters, and it is not a cryptobenthic fish. Okay, so when we plot the relationship between the year of description on the x-axis and the body size on the y-axis, because we assume that maybe smaller fish are being described later, then we get this hot mess right here. So this is the plot, x equals year, y equals length, and then a geom point. That's quite the atrocity. You can see there's basically nothing you can see. It's very, very dense down here. You can't quite see anything. And the reason for that is that length, for example, so body size, is a variable that is often distributed very poorly. So we have a couple of extreme values. So as a fish species here that gets to 400 centimeters, 4 meters. And then we have lots and lots of them that are way smaller than that. And that creates this massive skew in the data set that makes it really hard to plot. Now, luckily, we can easily adjust that. So here, all we've done is we've scaled this length variable based on the log 10, okay? And you can achieve that in a bunch of different ways, and I'll show you one here, which is the option where we simply scale the axis based on the log 10. You could also transform the values first and then plot them. Very similar effect, or it shows the exact same thing, but the axis will look different. Note that there is no log of NAs. There are some NA values where species don't have a length associated with them. So what we're doing is we're just dropping those NAs just to be cautious right here. Then we're doing the exact same plot we did earlier, but then we're telling ggplot that we want the y-axis to be on the log 10, and that's this plus scale y log 10. And what we can see is much prettier than the previous one. Just for comparison, this is what it looked earlier. This is what it looks like now. And we can see that there's actually a really nice sort of relationship where the smaller the species, the later they are being described. We can also adjust the axis labels and the tick marks. And what I've done here, cheekily, I have flipped around the length and the year. So now length is on the x-axis and the year is on the y-axis. It's the exact same data, but it's just flipped around, just for kicks. And what I'm doing here, again, from here to here is more or less the same. And then I'm saying scale y continuous. And I'm basically telling it to go in 20-year steps. So in the previous plot, we just had 50-year steps. I wanted a little more resolution. So now I've gone to these 20-year steps. And this is right here. So I'm telling the axis first what limits I want. So I'm going still from 1755 to 2015. And then I'm telling it where the breaks should be. And this is the old sequence function that you may recall from the earliest narration, and we're basically telling it that we want it to go from 1755 to 2015 in 20 year intervals. So that's really nice. And then I'm also telling it to pull those tick marks outside, which is something that you may choose. Oh no, actually, sorry. This is just the log ticks. I've changed the way these log ticks look to be increasing in size. And then we can also change the labeling of these axes. That's very simple, and it's more or less the same plot as earlier, except I've also changed the color because I like colors other than black. And I've changed the theme to be theme classic because I like the theme classic. And then we have xlab right here, and this always needs to be in quotes. So if you're basically telling it what words to print on the graph, it needs to be in quotes. We have body length in centimeters on the x-axis and year of description on the y-axis, and it changed those labels accordingly. If you have units that are really difficult, or Greek expressions or letters or something, it becomes a little more difficult, but that's something we can work through later. For now, it's easy enough to just relabel these axes. Okay, and then we can also work with, if we have different color groupings, for example, we can work with the legend that automatically appears on the side right here. So in this case, exact same plot, but I've added color equals category to this. So now the points are colored by the category, whether they're cryptobenthic or mobile. And everything else is the same, but then down here, I'm giving it a different color scheme. I'm working again with the Trimolantana color palette. And then I'm specifying what I want the legend to be like. So I'm specifying the label here, the name here, which is fish category. You can see how that translates to the legend over here. And then the labels, which is cryptobenthic and mobile. So again, very nice. This is actually a really nice looking plot. I would be happy to have that in a publication. And then we can also combine multiple plots. So that's something that is often very useful if you're making multiple plots, but you want them in one figure. Well, yeah, you could go into PowerPoint or some other software to stitch them together, but it's much nicer to just do it in R, and we can use the patchwork package to do that. If you don't have it, you have to load it into your library, install it and load it into your library. And it takes very simple syntax to combine different plots. So if we create a new plot here, P8, and then we say P6 and then the /P7, that tells Patchwork that I want P6 and P7 combined and arranged vertically, so one below the other. And then I've added this plus plot annotation tag levels equals A, and that actually gives me these letters here, which are really nice. If you're doing a multi-panel figure, you can use these tag levels here to specify how you want this. I could also use 1 or 2, or I could use a capital A. So quite nice. And that is basically it for the plotting. We can go through a last set of exercises where we will use the refish data set, and we can first create a box plot with family on the y-axis and length on the x-axis, with the x-axis log scaled. So again, we have length there, so log scaling is probably a good idea. We can fill these boxes based on category, and we will do that using the Hypsipops rubicundus color palette from the Visualize package. In case you don't recognize that name, if you're from the West Coast, from California, that's the Garibaldi, a small damselfish that is beautifully colored. And then we will also change the theme of that plot to theme _BW, that's a black and white scheme, rename the axis labels to refish family, and length in centimeters. I'd encourage you to stop right here and do the exercises. But here are the solutions. So solution 433A is here we're doing a ggplot where data is refish, x is length, and y is family. And we want a geom box plot, and we want the x-axis to be on the log 10. So this is what the plot looks like. Note that it gives me a warning here. This is the same issue that I mentioned earlier. There are some NA values in the length data, and ggplot is very smart. It just removes them. So 561 rows that don't have a length value, and ggplot just sort of skipped over that. All right, then adding the fill for category, which is either cryptobenthic or mobile. And we can see that a lot of these lower values are blue boxes, and a lot of the other ones are red boxes. So that suggests that the cryptobenthics generally are smaller, as they should be. And that was just done using the scale fish D with option equals Hypsipops rubicundus. And then finally, we just use the theme _BW theme, and then we rename those two axes, and we are done. So, hopefully this is sort of slowly seeping in, where you see things in ggplot annotation. It takes a while to wrap your head around it, but I promise you will not regret learning how to work around in ggplot. It is hands down the most powerful way of plotting data in R, in my opinion. And with that, we're at the end of this narration, and I hope you learned something, and I'll see you next time around.